Hello, ladies and gentlemen. So now I'm going to state for you the rational roots theorem. And before I mention it, I want to put it into context again. We know when we have like a linear equation, like let's say 3x plus 5 equals 8, right? We know we can directly solve it using the algebraic and arithmetic techniques we've seen so far. If we have a quadratic equation, we also know that there is a whole collection of techniques that we can use that we can that are guaranteed to give us a solution to that quadratic. And basically, it's a hard and fast rule that we can apply to any quadratic. If it's factorable, we can factor it. If it's not factorable, we can go straight to completing the square or the quadratic formula, which are essentially the same thing. And the problem, though, becomes when we're looking at polynomials with a degree that is greater than 2. Although it is true that there is a so-called cubic formula and a quartic formula, that is explicit formulas like the quadratic formula for cubic polynomials and fourth order polynomials, they're unwieldy, and that's why they're not usually taught, okay? But in any case, they don't help us with any polynomials that are greater than power 4, right? And so to solve polynomials that are greater than 2, we need to have a different approach. Now, unfortunately, there is no approach that works for all of them, okay? But so if we were to try to guess solutions, it would help us if we have a nice list from which to guess, okay? And so the rational roots theorem falls into this category, okay? Basically, it gives us a list of numbers we can check to see if the solution will have, if the polynomial equation that will look like this, we'll talk about it in a moment, has solutions of a particularly nice form. Okay, so let's read it together and let's see what it tells us. So suppose that we want to solve a polynomial equation of the form like this: a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 all the way to a1x plus a0 equals 0. So we're trying to solve this equation where the polynomial is set equal to 0. Okay? So, and also where each of the coefficients is an integer. That is a sub I, so the an minus 1, the an minus 2, the a1, the a0, where a sub I is an integer for all the possible indices, the 0, the 1, 2, 3, etc., all the way to n. Now here's what it's going to tell us. If the polynomial has rational roots, that is, if there are solutions x to this polynomial which are rational, then they are of the form this, p over q, where the p is a factor of the constant term a naught, the constant term of the polynomial, and the q is a factor of the leading coefficient a n, right? The coefficient of the term with the largest degree. Okay? So look what it tells us. It tells us that if this polynomial equation, okay, has a solution that is rational, a fraction or a whole number, then that solution must be in the list that is generated by taking all the factors of a naught and all the factors of the leading coefficient a n. You can make a list of those factors, and now we have a finite list of possible choices to choose from. Okay, so that's a huge improvement. We went from a polynomial where there's no general technique to solve to a list of nice possibilities for roots, and a list of nice candidates for roots of that polynomial. Okay? Of course, this theorem does not say that the polynomial has any real roots at all. It doesn't. It's possible that the polynomial may only have complex roots. It's possible that the polynomial only has rational roots. Okay, so this theorem doesn't tell us what kind of roots the polynomial has. Okay, but what it does say is that for any polynomial equation that can be written in this form, where the coefficients are integers, then if the polynomial has rational roots, if the x's, in other words, that make this equation true are rational, okay, then they are going to be of this form. And so by making an explicit list, we can take a problem that originally had no, basically we would be guessing and checking. In other words, and we know that there are infinitely many numbers to guess and check from if we're thinking about the real numbers. We went from a problem where we would have to guess infinitely many choices to try and find the zero. We now, with this theorem, are able to whittle them down to a manageable list. And I should say manageable in quotation marks, because it may not be that manageable, but it's much better to have a finite list than to have an infinite list. And so that's the advantage of the rational roots theorem. And of course, when the polynomial does have rational roots, we'll be able to find them from among this list. Okay? And so that's what we're about to do in the following examples. And I hope you have enjoyed this initial discussion. And let's proceed with examples right away. Thank you.